Hi, this is the presentation for advanced computer concepts, and the main goal for this presentation is analyzing and implementing some algorithm regarding search engine. The instructor of this course is Dr. Mehdi. This presentation and code have been implemented and provided with two members. Each of us implement 3 features. The first concept is what is a search engine. Search engine allow users to search the internet for content using keywords. Search engine often change their algorithms to improve user experience. They aim to understand how users search and give them the best answer to their query, giving priority to the highest quality and most relevant pages. Other goal for a good search engine. The first algorithm is symbol graph. Actually, it represents an undirected graph, providing mapping between strings, vertex names, and integers, and it serves as a wrapper around the graph data type. Also, it supports initializing a symbol graph from a file, and for this purpose, it uses a specific delimiter to split nodes, and each line in the file contains the name of a vertex. The other concept is regular expression. A regular expression is a sequence of characters that forms a search pattern. When you search for data in a text, you can use this search pattern to describe what you are searching for. So with these two concepts, here I implemented this search. It's a combination of symbol graph and regular expression. Based on the input, it changed the type of search and using different methods for search. Go to A. We have a file of movies. You can see here it's a big file with a lot of information. Consists of the name of films and the name of actors and actresses who played in those films, and also the construction dates for each film. And the delimiter for this file is this character, and each line in the file contains the name of a vertex. We input a name of a character, an actor actually, and then the list of films that, for example, Brad Pitt, and here you can see the list of all films that this actor has been played. For this part, I used a symbol graph algorithm, and if the user enter a number, for example 2002, and enter, the list of all films which were constructed in this year can be would be listed here. For this part, I used a regular expression. If I go to codes here, you can see here there is a if condition, and it check if it's number. It means that it's the year. It means it's a year, and so the type of search would be like this. Here it based on the the pattern that we had to provide for search. There is a string before the year, and also the year is wrapping with a parentheses. So this pattern had been written, and it's sent to compile method, and then the matcher and send this and call matcher method, and then a list of all find items can be written in the console. The second type is the second method of search will be called when the input is a string. So here we define a delimiter based on the file, and then we have to change a bit the input because of the file's pattern, and then pass the input to the here we use pass input here in the method, and here we initialize a symbol graph instance, and also pass the result to this method. And in here it checks that if the vertex is found or not, and then if it found, it's printed the result in the console. The other feature is extract HTML from website. Actually, extracting the full HTML enable you to have all the information of a web page. Fetch and parsing the HTML document from the web and find data within it. For this purpose, we used a JSON library. Actually, it's a Java library for working with real-world HTML. By this library, we can fetching URLs and extracting and manipulating data by using HTML5 DOM methods and CSS selectors. Here, if I go to codes, the second feature is extracting data from HTML. We have a folder here and a file, and there's a list of URLs, and we can add another URL, for example this URL here, and based on these URLs, the method call each of them and then extract them here in this folder. If I go to this part, and let me stop and start to clear the. If I go to B, you can see that all the URLs have been extracted, and when I refresh this folder, you can see all the files related to this URL, and the content of these files are text. If I go to codes, here you can see that we get the files from this file, and then read the content of this file line by line, and then check if each line is a URL, then save the web content in the cache file. Here we call the JSON connect method, JSON library, and then connect to URL, and then get the body of this document and save it in the to the new file that we have created here. And the result of this feature will be used in the next feature that I have implemented. Let's go to slides, and here the brute force algorithm is the next feature. Its duty is finding a substring by checking all of its possible position. The algorithm embedded knowledge of the problem, which makes it therefore either dull or brute. Here, as you can see, the construction of this algorithm is that starting from first letter of the text and the first letter of the pattern, check whether these two letters are equal. If it is, then check second letters of the text and pattern. If it is not equal, then move first letter of the pattern to the second letter of the text, then check these two letters. This is the simple technology everyone can adopt. If I go to codes here, we go to this folder and give all the files in this folder and check them one by one. Here we use a string builder and save all the content of these files in a string builder, and then send this string builder to the brute force matcher algorithm. Actually, it's the algorithm that I have explained the functionality of this in the slides. Check each character one by one to find the matching result, and when the matching index list field, then we check if it's okay. It's empty. We print that there is no item that found. Otherwise, we print the result one by one and the position of those results. For example, I show the result in C. For example, I enter unknown data, and you can see that there is no item found. But if I put a meaningful, for example, test, you can see that we have, for example, the other word is. You can see all the results here. Okay, thank you. Tarun, please.
Okay, so the next part of our project is searching the keyword in the HTML text files which we converted earlier using Moore's algorithm. So why we use Moore's algorithm is because it is one of the most efficient string matching algorithm, and it has a time complexity of big of m star n, where m is the length of the pattern and n is the length of the text. So the time complexity reduces to big of n when the substring is not present in the text we need to search. Also, Moore's algorithm searches for a substring from the right to the left. This algorithm can be implemented in two ways. One is bad character approach and the other is good suffix approach. So bad character approach is whenever we find a mismatch in the substring and the string, we're gonna shift the substring by an offset. So we're gonna get the value of the offset by using the bad match table. If there is no value in the bad match table, then we're gonna shift the whole pattern with the length of m. So how do we calculate the bad match table? So before executing Moore's algorithm, pre-processing for Moore's algorithm is essential. So that is by constructing a bad match table. So bad match table uses a general formula of max of 1, or the length of the pattern minus the index of that particular character minus 1. So let us take an example. Team mast is a pattern that we need to search for, and it has a string length of 8. So at T, if you want to have a bad match table, the value is going to be length of the pattern minus the index. So that is 8 minus 0, 8. But when it comes to E, we're going to use the formula max of 1, comma length of the pattern minus the index minus 1, since it is the second character of the string. So that in our case is 8 minus 1, which is the index, and minus 1 according to the formula. So that is 6. So similarly, we consider the formula for all the other characters of the pattern and then form a bad match table. So there is also a letter called star. So that is to represent if there is any other character to the considering a mismatch. So the T as well as the star is considered the same. So the star is also given the value of T, that is the length of the string. So whenever the first character or the last character or a character which is not present in the pattern is a mismatch, then we're going to shift the whole string by the length of M as said earlier. So that is going to be 8 in our case. Coming to the searching. So welcome to team mast is the text that is given to me, and tmast is a keyword that we have entered. So if we search the pattern S, so that will be a mismatch to E, since the MooreAlgorithm algorithm searches from right to left. Since T is a match, we're gonna go with S. So S is a mismatch to E. So the alphabet that it caused mismatch is E. So we're gonna go to the bad match table, find the value for E, which is 6 in our case, and move 6 values to the right. So once we moved 6 values to the right, we're gonna compare from the right to the left again. So that is going to be T, which is mismatched with M. So we're gonna look up for the value of M to get the offset value. So that is going to be 3 in our case. So we're gonna move 3 spaces to the right. We're gonna move the substring 3 spaces to the right. So then hence the pattern is matched, since it goes from T, S, A, M, M, A, E, and T. So this is how the searching is performed in Moore's algorithm with bad character approach. So coming to the next feature we have implemented, that is suggesting the nearby keywords. So the basics of suggesting nearby keywords is by using distance between the given keyword and the list of keywords in the dictionary. So how this is calculated is by using Levenstein's distance in our case, but it can also be calculated by other distance formulas present. But Levenstein's distance, I felt it is effective, and it also uses dynamic programming. So it has a formula where if it is a match, it's going to take the tail of A or B when it's a match, and if it is not a match, it's going to take minimum of replacement, deletion, and insertion values and add 1 to them. So the insertion, deletion, and the replacement values are the if I'm sorry for that. So let us just take 2 strings. One is Saturday and one is Sunday, and we're gonna derive a Levenstein's distance table for it. So the first row is gonna be 0, and for S it's gonna be 1, 2, 3, 4, 5, 6, 7, and an 8, based on the index and how many characters we need to replace for, or maybe insert for that null string. Similarly, for the Sunday, when there is a null string, we're gonna need 0, 1, 2, 3, 4, 5, 6 inserts to get the whole string called Sunday. However, if you want to compare these 2 strings and need how many operations to change one to the other, so it's going to be S and an S, so it's a match. So we do not require any other insertion or deletion, so it's just the same string. So it's going to be 0 and a 0. But when we match S with an A, we're gonna need a deletion and an insertion over here. So the deletion is going to be 0, So the minimum of replacement, insertion, and deletion is going to be 0. So we're going to take 0, add 1 to it, so we're going to get 1. Similarly for S with T, we're going to take minimum of 1, 2, 3, and add 1 to it. So that's going to be 2. And similarly with 3, 4, 5, 6, and 7. Coming to the next character, that is U, it's going to be 2. Why this is 1, meaning we're going to take minimum of 1, replacement, 0 as the insert, and 2 as the deletion. So that is 0. We're going to add 1 to the 0, that being 1. And coming to the next, we're going to match U with A. So it's going to be minimum of replacement, deletion, and insertion, and add 1 to it. So which in our case is 0, and we're going to add 1 to it, so it becomes 1. So similarly, all this table is filled in that particular format, and we're going to get the ideal distances on number of operations we need to convert this string to the other and get the distance respectively, and suggest the close words based on that. So for this, the ideal distance of S would be 0, S to S in Sunday and Saturday would be 0, SA to SU, SA to S would be 1, S to T would be 2. Similarly for the other, so if we're gonna increment the pattern with Saturday and Sunday, it's gonna be 3. So the Levenstein's distance is 3 for it, and if we do not have any other word which is closer than this, if we type in the phrase Saturday, we're gonna get Sunday. So this is how Levenstein's distance is used in our project. So let me just show a quick demo on how our project executes. All right, so this is the main function. Over here, once we go and run the main function, we're going to get all the features and their respective options which we need to choose to enable them. So let's start with the first one which I have implemented, that is keyword search using Moore's algorithm, search algorithm. So that's going to be D in our case. So what does small database exist means is nothing but we're going to create a small database of HTML files in W3C web page database. We're going to take them, we're going to convert the HTML files to the text files. Since I've already run this program earlier, I have the small database setup. If not, I'm going to get the acknowledgement message called done. So coming to the keyword search, let's just give Java in our case. So they should give me search results by using Moore's search algorithm based on all these web pages on the left, which are converted into text files and are parsed to get the word Java. This is going to take a minute to search all the text files. Okay, so displaying these results is going to be in a way that all the file name will be present, and the file name is present, that is mobile web application best practices.html, and the text equal to 47624 is nothing but at what offset did the algorithm find the particular keyword Java in our case. So all these web pages are displayed in an alphabetical order. So M goes first, followed by R, S, T, and W. And similarly for each web page, we're gonna get at which offset did we find the keyword Java. Coming to the next feature, that is suggest close words. So we're gonna need to enter a word over here. Let's just enter TT. So the closest words for TET are TEAT, TELT, TENT, TEST, and TRET. So how this thing has processed this request is by using Levenstein's distance, but the dictionary of words it went through is in dictionary.txt. So this file consists around, there are many words, plenty of words. So it parses all these words to get the closest 5 words in that particular dictionary, and sort them from the closest to the farthest word. So for this, I'm going to use Lucene as Apache's Lucene library for checking for getting the Levenstein's distance, and suggestion number is 5. So I'm going to get 5 words which are closest to the keyword which I've entered. And if there is no word that is close to the keyword which I've entered, then we're going to display an output message called no suggestions found for the word. Last but not least, the final feature which is present in our search engine is scrape for email and mobile numbers present in the particular web page. So that's going to be F option. So again, we're going to parse these HTML files, convert them to the text files, and we're going to need to enter the page URL. So the page URL is going to be, let's just take this. So the page URL is going to be the whole about W3C standards.html. I'm going to copy this. I'm going to paste it over here. Okay, so I'm going to get the phone numbers present in this particular web page are these two, and the emails that are present are this and this. So coming to how we did this is by using simple regular expression to scrape a web page. So what I do is I go to the particular web page. I put all the text into a stream, and then search for a pattern where this regular expression exists and extract it, and then print the number in a loop and the emails in a loop. So before that, all this is by converting the web pages into text files before I need to put them into a stream and then search for the pattern. So coming back to the presentation. So the future work that is left is we can implement an interface for better interaction and for better user experience, and we can also use advanced web crawling since we have only a few hundreds of web pages right now. So we can use more web pages to make the search more better, and also implement more searching algorithms such as page ranks to display the results more accurately. So thank you. So these are the references we followed.